Hey everybody. Today we're talking about the sampling distribution of sample variance. We're in a situation where we're repeatedly taking samples of the same size from a normal distribution, taking the variance of each, and asking what sort of distribution we get when we look at all of those sample variances at once. Let's start just by doing an example, like a demonstration. We're going to take samples of size 5 repeatedly from a standard normal distribution. Each time we're going to compute the sample variance and then we'll plot the results. Since we know the variance of the standard normal distribution, it's 1, we expect that the sample variance for those samples of size 5 will be 1 on average, though sometimes it'll be a little higher, sometimes it'll be a little lower. Now, negative variances are not possible, so whatever distribution we get, we should not expect it to be a normal distribution. So here's some R code that takes samples of size 5 1,000 times from that standard normal. It calculates the sample variance each time and saves it in a vector called V. Here's a plot of the results. And you can see this histogram looks a lot like a chi-squared distribution. That's not a coincidence. Here's the fact that encapsulates that observation. If we're taking samples of size n from a normal distribution with fixed mean and variance, then the sample variance, call it s squared, has this relation. We take s squared multiplied by n minus 1, 1 less than the sample size, divide by sigma squared, the variance of the normal distribution we're sampling from, and the resulting random variable has a chi-squared distribution with n minus 1 degrees of freedom. So when you're thinking about sample variance, you're thinking about something that has more or less a chi-squared distribution. Now, a really important warning here is that this fact is assuming we're sampling from a normal distribution. There's no kind of central limit theorem in play here, though, so if you're not sampling from a normal distribution, all bets are off. The distribution of s squared won't have that chi-squared distribution, and if the sample size gets larger, you cannot assume that the distribution is going to converge to a chi-squared distribution. All right, let's do an example. Lengths of a certain kind of screw are normally distributed with mean 1.8 centimeters and standard deviation 0.25 centimeters. Describe the distribution of the sample variance in samples of size 50, and then compute the probability that the sample standard deviation is greater than 0.30, which is to say that the sample variance is greater than 0.09. As always, I recommend pausing the video, trying this one on your own before seeing my solution. Of course, the idea is to apply that fact, and in order to do that, we have to take the sample variance, s squared, multiplied by n minus 1, and divide by sigma squared. And so that quantity then is going to have a chi-squared distribution with 49 degrees of freedom. Now we can try and do some probability calculations using s squared. The way that we'll do that is by taking the probability statement that we're interested in, the probability that s squared is greater than 0.09, and then multiplying both sides of that inequality by 49 over 0.25 squared to get a probability statement involving a distribution that we know. If we call the fraction on the left side of that inequality u, then we're looking at the probability that u is greater than 70.56 in chi-squared of 49. 70.56 being 49 divided by 0.25 squared times 0.09. That probability is about 2.3%, which I got using the R code 1 minus p chi-squared 70.56 comma 49. Let's do one more example. A sample of size 100 is drawn from a normal distribution with unknown parameters. So in this case, we don't know the variance of that normal distribution. Let's use the sample to compute a level 90% confidence interval for that unknown variance. In other words, values a and b such that the probability that a is less than sigma squared less than b is 90%. We're going to use the fact once again. We're going to start with the sample variance and scale it so that we have a random variable with a truly known distribution, chi-squared of 99. We do that by taking the sample variance, multiplying by 99, that's n minus 1, and dividing by sigma squared. And just in this case, we don't know sigma squared. We're now in chi-squared of 99, so we're going to be able to do computations in a known distribution to find the values c and d so that that random variable, the probability that that random variable is between c and d is 90%. The most obvious choices here are the 5th and 95th percentiles of that distribution, though of course we could use others, like the 4th and 94th include 90% of the probability between them as well. We can compute the 5th and 95th percentiles of this distribution directly. I did it using R, using the chi-squared command. You can see the code here. So now I'm going to take C and D in this probability statement that you're seeing in the middle, plug in the values of C and D that I have, and then solve it for sigma squared, like this. First, I'm going to divide this entire inequality by 99s squared. That's how I'm getting to the middle line there. And then I'm going to take reciprocals of each piece to get the bottom line. Remember, when you take reciprocals with inequalities, you have to reverse the sense of the inequality. I'm going to then turn around all the inequalities so this actually looks a bit more like a confidence interval. I'm getting the probability that 0.803 s squared is less than sigma squared is less than 1.285 s squared is 90%. And so those two endpoints that we're seeing there to the left and right of sigma squared are going to represent our confidence interval. In a given sample, we'll get an actual value of s squared and be able to compute numeric endpoints for that confidence interval. For instance, if we have s squared is 5, then just plugging in, we get the confidence interval 4.017, comma 6.424. And that's the 90% confidence interval that we're looking for here.